Hello, everyone. Thank you for having me here. I was informed that it should be a lecture for students, and I didn't know what sort of students and what would be your background. So I assumed that there is not much of a undergraduate or graduate training on compressible Navier-Stokes equations. And I'm going to make like an introductory crash course through the theory of compressible Navier-Stokes equations. And I will leave you with a few problems which are still fundamental, very difficult, and where young, talented I should contribute. All right, so just to fix the notation, I'm going to write the equations of conservation of mass and conservation of linear momentum for the fluid. So for the purpose of this talk, the fluid is always in constant temperature. So heat conductivity effects are omitted. So that's the density. There's a time derivative of the density. I will be very sloppy with formulating everything precisely because we could dwell on the definitions along here. And I don't want to do it. I want to give you the overview of the techniques that are used and where are the bottlenecks of what's happening here. So I'm writing the Newton laws for conservation of mass. Rho is the density. And linear momentum, u is the velocity, rho u is the momentum. And then my fluid is compressible, which means that I can even add some force to the right-hand side, which means that I have the compressibility effect expressed in the continuity equation. So the velocity vector field is not divergence-free. There is a compression due to the fact that you can expand a certain volume of the flow. So now rho is a scalar, right? Rho is unknown. It is a scalar. It is a scalar from our time-space domain, taking values in R plus, where R plus denotes for me 0 included, so we can't avoid vacuum, and that's important. And the other unknown, on Blackboard it's difficult to distinguish scalars from the vector, but this is a vector, again, on some domain to R3. Okay, so we will be in the physical space. U is a three-dimensional vector. We look at this equation, and we see that there are 1, 2, 3, 4 unknowns here. And there is a fifth one, with P, which is called the pressure. P is the pressure. And of course, it cannot be unknown because you have only 4 equations. One, an equation for each component of the velocity vector field. So P should be a given function. And indeed, what I'm going to consider today is P of rho equal to rho to the power gamma. So it is explicitly given function of density, where gamma is strictly larger than 1, and it's corresponding, if you had any course of physics before, to the adiabatic exponent of the gas or fluid in general. S is the stress tensor. And in this case, I wrote the equations in the so-called conservative form. So if I integrate this equation, you'll see that the integral over the space of this object, so the total momentum, is a constant of time. Yeah, so it is equal to the initial value. The stress tensor is in the divergence form. But in general, this stress tensor, for the purposes of today's talk, is something like a Laplacian of the velocity. I'm not going to talk about physical meaning of it. So I will assume that the divergence of S can be expressed as mu Laplacian of u plus diagonal component, so gradient divergence of u. Yeah. So it is a little bit more general than just Laplacian of U. It will be a little bit more general than just parabolic equation for the reasons of invariance of the motion of the fluid. Okay, but yes, this is the form, and I'm not going to explain that much. This equation tells you that acceleration of the fluid, like acceleration of the motion of any rigid body, is due to sum of forces. And these are the forces that correspond to deformation of the fluids. These two forces, gradient of the pressure and divergence of the stress tensor. The notation is the following one. This object here is a tensorial product, vector product, let's say. So it is UI, UJ matrix. Divergence is summation over the row of this matrix. So we have vectorial equation, PDE. Yeah? All right. So here we have our system. F can be whatever you want, really. It can be gravitational force. It can be whatever you want to add to the system. Maybe you want to have influence of the motion by Coriolis force, any external factor, but it can be also random component or some stochastic component in the fluid. And indeed, there's a lot of literature on that as well. So this lecture is going to be about prehistory and with information about what happened since then. The big names that I should mention before I actually enter into details is that this is a highly nonlinear system of equations, of conservation laws, hyperbolic and parabolic, combination of the two. And therefore, I don't know if you had a course on PDEs, but I suppose everybody knows what Berger's equation is. We expect development of shocks, discontinuities, really, of the solution in a finite time. No matter how smooth the data is, right? If we don't restrict something in that system, and then we expect these formations of shock to happen. Moreover, as you see, I have indicated already that the density is going to be touching vacuum. And in fact, this will happen because this equation doesn't have any regularizing effect. It's just a hyperbolic equation. And when density touches vacuum, you see that you kind of lose information about velocity coming from the time derivative. On vacuum, this time derivative is not defined, and you kind of degenerate the second equation as well. All right? So this is a problem, but it's not the biggest problem of this theory. So let me say a little bit about the existence of solutions to this problem. Well, I know this problem is not defined right now. I didn't prescribe initial condition yet. I didn't say anything about boundary, data, nothing like that. So, as I said, I'm going to be very, very sloppy here. I will only prescribe rho to be equal to, let's say, time to be equal to some rho 0, and velocity, although I should actually prescribe the whole momentum, is going to be something like m0. So this is my initial data, and now omega, this can be really a lot of objects. So I'm not going to, although in my head I'm always going to justify all integrations as if it was torus, but you can think about it as bounded domain, bounded Lipschitz domain. You can think about external domain. This is the project that we do with Bogusov right now. So exterior of some bounded domain. Or you can think about the whole R3. I'm choosing 3 for simplicity, but the whole theory, of course, works for dimension 2 as well. So, but in particular, it also works for torus. Let's say 3-dimensional torus, and this is the simplest case that I'm going to discuss today. Depending on which of domain you choose, you need to supplement the system with boundary conditions. And you can either impose boundary conditions, so these are always imposed on you. So you can take either Dirichlet or Neumann boundary condition, or the so-called friction, which is a mixture boundary condition. There are also people considering these problems on the moving domains, or problems like that on manifolds, especially at the University of Warwick, where I work at the moment. Now, because of this kind of, well, it's hard to explain it to the students, but this analogy to Berger's equation, we really don't expect smooth solutions to prevail during the time. And I'm going to look for solutions in the framework of weak solutions, okay? So weak solutions require ordered quantities appearing in the equation to make sense in the distributional setting, right? In the weak form. And this is a theory I'm going to talk about today. So the theory of weak solutions is due to Pierre-Louis Lyons. Pierre-Louis Lyons, the son of Jacques-Louis Lyons, who got his Fields Medal, I think, in the 90s. I don't remember, it was 1996 or 1998, for exactly this contribution. So Pierre-Louis Lyons' existence of weak solutions to bulk of problems, including time-dependent, independent, stationary problems. I think there are even, if you look at his book, there are 2 volumes. So he even has some remarks about periodic solutions and many, many other problems, including singular limits and so on and so forth. He also wrote a chapter on the incompressible fluids, but the compressible one is something that I'm interested in, 98. What I wanted to highlight is that his theory works for exponent gamma larger, actually only larger, although he claims it's equal as well, 9/5. But there is some problem in to cover the exact exponent. So you see that we are quite far away from 1. And this gamma, not only that it should be larger than 1, but it should be close to 1. It is minimally larger than 1 normally. So now in 2001, there was another big contribution in this theory, and this is to Edward Feiereisel, where he combined the Lyons, well, I wouldn't say that he combined the Lyons approach, but he improved this approach by modifying the last step of the approximation, and he removed this assumption. And for him, gamma is larger than 5/3. Yeah? So you see that we crawl back to 1, but very, very slowly. And we are not yet there. And I would say that this is the best result. There are results lowering gamma in some other frameworks of solutions, like measured value solutions, right? Or in if there is a stochastic component, and we consider a little bit different notion of solutions. But for weak solutions, removing these assumptions, going to, in particular, removing the assumption gamma larger than 3/2, which seems to be critical assumption for convective term to be integrable even in this framework. This is the first big problem that I wanted to leave for young people. Can you lower this exponent? And now I wanted to explain you what is the problem with lowering this exponent and why it was so difficult for the decades now of mathematicians working on that problem. So I will not overthrow you with literature. These 2 references are excellent, and both of these artists have monographs really on that matter. So please feel free. So why is it difficult? To understand it a little bit, I wanted to explain you what a modern proof of existence of solutions for nonlinear systems of PDEs or coupled system of PDEs is. So when you see the system for the first time and you understand a little bit of physics behind it, not much, I don't understand much, then the first question is, you want to prove the solution, and you need to understand what would be your notion of the solution, right? And the way to do it is to understand what quantities are conserved. So I already told you about conservation of mass, conservation of momentum, But there is another quantity, very important in physics, and this is conservation of energy, obviously, right? So even for mathematicians, we know the concept of energy because, I don't know, calculus of variation, for example, right? So there is a conservation of energy, and once you figure out what conservation of energy for that system is, it will nicely show you what kind of estimates you have in this system. And this estimates, right, energy is something like U squared plus some potential energy. And this estimates will indicate to you what is the framework, whether these terms make sense or not, and in which form, yeah? So that's the first part of the modern proof, like even figure out what is a possible framework of solutions. Today I'm going to talk about weak solutions, but tomorrow I'm going to talk about very weak solutions, like measured valued solutions, or duality solutions, where you cannot really identify what the flux is, yeah, for scalar conservation loss. The second step of the existence of solutions is the so-called topological stability of solutions, of this definition. So now you make this kind of experiment in your head. You have this a priori estimates, and you imagine that you somehow constructed the sequence of solutions that satisfies this set of a priori estimates. Yeah? God-given sequence of solutions that satisfies these estimates. Can you show that this sequence of solutions converges to another object that is again a solution according to the definition that you cooked up in the first step? Okay? So it's some kind of sequential compactness, yeah, of the definition. All right, so this is point number 2, and I would say it is the essence of the proof of existence of solutions because it contains all the compactness techniques that we are going to use in the whole proof. The last thing, the tidying up of the house, really, is to construct a sequence of approximate solutions. And that is a very long, usually, procedure, multi-level construction. Go away. I have my fan club over there. So this is a multi-level construction procedure that involves adding to the system parameters, some parameters that regularize it. So why do we do it? Because as mathematicians, we really don't know that much about solutions of PDEs. The only PDEs that have solutions, and we can really take them to our hand, see their properties and so on, there are not so many of them. You will learn about 4 of them, maybe. Transport, heat equation, right? Poisson equation, and maybe wave equation. Classical solutions, right? And with those objects, we really know what to do. We have explicit solutions, etc. I'm talking about multi-D situation. So we kind of want to use this intuition that we have from this very simple linear PDEs, not very simple, but linear PDEs, and try to approximate our system with those. It happens in a couple of stages because there are many of nonlinearities in the system, and that is very technically heavy procedure to approximate the system. I'm talking about it because the contribution of Edward Fairazzo, it is a great contribution, but it is at this very last stage of approximation of the solutions. He came up with nice, interesting truncations of the functions, an extension of the Di-Pernod-Lyons transport theory that allowed to lower this exponent. Why it is difficult? Why it is problematic, this exponent? Well, when you look at the system, it is kind of easy to see that the bigger gamma is, the stronger nonlinearity is in the system, at least with respect to the density, right? If gamma is very large, this is more and more nonlinear, in the sense, further away from the linearity. And if you think about weak solutions, you probably will have some weak conversions leading to this weak solution. And you know that combination of the nonlinearity and weakly converging sequences is always tricky, right? We don't commute these operations at all. We need to have something stronger. This nonlinearity here is especially difficult to handle because density, yeah, this is a function of density now. satisfies only a hyperbolic equation, and there is no regularizing effect in this equation. There is no Laplacian. There's nothing that resembles heat equation here. Okay, so if there is some kind of even if you start from regular solutions, you will end up in something that has discontinuities, that has all these problems. So on one hand, bigger gamma, bigger problems, but on the other hand, bigger gamma means that you control, later on when we do energy estimate, you control better norms of the density. So the higher gamma, the bigger LP, P exponent in your LP spaces where this is integrable, and that's a winning factor, I would say, because it controls the nonlinearity there. Yeah? So there's certain things that can be done only for big gammas. The other nonlinearity, which is tricky, is this convective term. It's a quadratic nonlinearity with respect to velocity, but for this, we have very nice compactness methods, provided that the stress tensor is of that form. Okay, so to the point. The rest of this lecture will be devoted to step 2 of the proof of existence solutions, and this is called the weak sequential stability of solutions. In the sense that I mentioned, I want to construct a sequence of solutions, I want to show compactness of some sequence of approximated solutions that I don't know how to construct. But let's look at the a priori estimates. Well, there are a few of them. Already, you know that the conservation of mass is a natural consequence of the first equation. You just, let's say, integrate this with respect to space over some domain omega. If you have 0 Dirichlet condition for velocity, the boundary term vanishes. If you have torus or periodic box, whatever you like to work with, this also vanishes. And you have dt of the integral of rho, at least in the framework of classical solutions. So assuming that everything has enough of regularity, so something like that is equal to 0, which means that if you now integrate with respect to time, the integral at any point of time is constant and equal to the initial mass. So you prescribe mass and you prescribe this integral everywhere for each time. Second conserved quantity is conservation of momentum. The same reason, I'm not going to write it because it's not going to be very useful for us. And the reason for that is that velocity u doesn't have a sign. It's a vector, and it can take values in R3. Okay, so that's not very interesting for me at the moment. I want to talk about conservation of energy. Was this lecture 1 hour and a half, I would probably derive it, but it's not difficult, it's simple exercise actually. What you need to do is multiply this equation now by u without any sign, and sum it up with continuity equation multiplied by u square. When you sum it up, what you obtain is that dt of the kinetic energy, so rho u square divided by 2, plus potential energy, and I will explain where it comes from, plus your stress tensor let's say that our force is equal to 0, that this is equal to 0. Again, for classical, I assume that rho and u have enough of regularity. This is this nice, smooth, approximate sequence for which I can justify everything. So I integrate over omega. Let's say omega is periodic in space. And now this comes from the transport derivative. From this term, the flux will integrate to 0. The potential energy, of course, has something to do with the pressure. the strength of nonlinearity gives us, again, nice estimates for the density here. And then there is a dissipation term. So I multiply by velocity u, I put divergence on the velocity, so I have S gradient u. This is a tensor, scalar product with another tensor, which is gradient of u. That's what we get. F is going to be equal to 0 from now on, okay? To simplify the calculations. So this is a conservation of energy. And having that only, I already can figure out that everything is in L1 in my system, at least in the weak sense, right? Because I know that the density is L infinity L1 function, right? From here, I deduce the density is rho n. Let's say I have the whole sequence, or let's call it epsilon, is uniformly bounded in L infinity L gamma, L1 first. So I don't know if you are familiar with this notation, but these are Bochner spaces. Of course, I'm sure that people use it here. So it is L infinity L1 function, but from here, gamma is larger than 1 strictly. I also know, integrating with respect to time, that density is L infinity L gamma function, right? So I'm going to write L gamma with respect to space because my domain might be unbounded, and then I want to keep L1 as 1. So this is the density. Now for the velocity, well, I don't know yet very much, but I know that let's say rho epsilon u epsilon is an L infinity L2 function with respect to space. So my square root of kinetic energy is here. And from here, using some sort of more generalized version of Korn inequality, because I kind of from here I have an estimate for the symmetric part of the gradient of the velocity. You will not see it right now why, but it's a formula for the stress tensor. So from here and from the information that I already control velocity on some subset, at least on some part of the domain, density cannot be equal to 0 because mass is non-zero. So from here, I know that there is some LP norm of velocity controlled, and I control the symmetric part of the gradient. All in all, I can say that u epsilon from here, u epsilon is uniformly bounded in L2, let's say W12. Okay, I control the whole W12 norm of the velocity from here. And only on the basis of that, I can show that everything is bounded in my system. Exercise for you is to understand for which values of gamma this object, rho u square, yes, is bounded in something better than L1. Yeah. We know that it's rho u square is bounded in L1 with respect to space because kinetic energy is bounded, but we want something better than L1 because, again, if we only have boundedness of L1 sequences approximating the solution, the limit doesn't have to be L1 object, right? We may end up with measure, there might be some concentration. Okay, so, but other than that, these sequences allow us to, these bounds allow us to control everything in at least L1. The problem is that, that for the density, it's L1 and that's it. So for the moment, we only have L gamma bound from the potential energy. And L1 is the least we have to control here to make sense that this term is integrable. But it will not allow you to pass to the limit in the term. Yeah, L1 bound for the term will not suffice. So there is a third estimate, a priori estimate, and I'll say improved pressure estimate, because you can do it in a couple of ways. So. First, we the idea is to extract information about the density, not from the equation for the density, but from the equation of momentum. And this information on the density is hidden here, right? So in order to extract this information, we kind of have to invert the divergence operation, right? So now imagine that you can test this equation by some test function, let's call it phi, whose divergence, when you put the gradient on the test function, it will be divergence of this function, whose divergence is some function of the density, right? Then you have rho to power gamma times some function of the density that you have thanks to inversion of the divergence operation. Yeah? And provided that you can control everything else in that system that comes from this testing with this special function, you can control the L gamma plus some theta norm of density straight from the continuity, from the momentum equation. And that's the idea of, this really depends on the domain that you are interested in, but the Bogowski operator would be one way to achieve it, to invert this divergence operation. So let's say Bogowski estimate, it's a jargon, but Bogowski type estimate. So you test by some test function whose divergence is equal to rho to some power theta, maybe let's subtract from this function an average, so spatial average of the density here. So you can show that you can construct this operator. It's a linear operator from LP to LP. This theta depends really on the choice of gamma, but for us, the only thing that matters is that theta will be something strictly bigger than 0. And unfortunately, you cannot do it usually up to the boundary because there is a problem with not sufficient boundary condition if you use something like that. And you usually test momentum equation with this test function phi, let's say phi of rho, this one here, but you always have to add some kind of cutoff function in time and cutoff function in space that brings you further away from the boundary. So in fact, this estimate gives you uniform bound, let's say from 0 to some capital T, over any compact set included in your domain for something like rho to power gamma plus theta dx dt. And this is happening for your sequence, which I denoted by epsilon at the bottom. So you can show that something like that is bounded by some constant which depends only on the initial data and the energy bounds of the initial data. Yeah. So that's the third crucial a priori estimate, and based on that, we will try to pass to the limit with epsilon. Yeah, in the next 10 minutes. So hold on tight. All right. So what do we know right now? A passage to the limit with epsilon. I often tell it to my students that the progress is not really solving the problem, but the progress is to identify what you don't understand about the problem, where the difficulty is. Yeah. Because if we had infinite amount of time, each one of us could solve any problem, but we need to understand which one to choose, which are interesting and which can lead to something. So from this a priori estimates, I can now extract a subsequence which will always be labeled with epsilon anyway. So I'm not going to write epsilon n, k, and so on. I will always denote it with the same letter, which gives me the convergences or weak convergences of the quantities that I'm interested in. So first of all, rho epsilon will converge to rho weakly, actually star because L infinity spaces are involved. So let's say we are on bounded domain, so it's L infinity L gamma. Right? And we also know that this convergence will happen weakly in L gamma. Let's say theta is equal to 1. So let's draw one more symbol. Gamma plus 1, but this is only local. In times, and actually we can improve the convergence in time, but let's say local in time space. Okay? Now, that's not the whole information about the velocity we have. Of course, from the a priori estimates, the L infinity L1 L gamma bound and L gamma plus 1 bound from Bogowski estimate. That would be it. But now what I can do is I can come back to the continuity equation and see that actually from here, from this equation, I can say something about the time derivative of the density, right? So in particular, I can say the time derivative of the density is bounded in some negative Sobolev space, right? Rho u will be bounded in some LP, but the divergence of rho u will be bounded in something like W minus 1 some P. And if I have the time derivative of the density bounded in dual to something that in which I have my L infinity norm of density bounded, I can improve this convergence to convergence in C with respect to time in, let's say, L gamma for the moment. But of course, it's not a strong convergence. Okay. It's not a strong convergence with respect to space because there is no mechanism to improve this convergence. It's a weak topology in L gamma spaces. So it converges in L with weak topology in L gamma. This is the notation. I don't like this weak sitting here. It should be here in my opinion, but people for some reason use it here. And I'm sticking to it for the purposes of today. All right, so it's a little bit better information, you agree, than a weak star convergence in L infinity. It's a strong information in time. Now, you can also read from the a priori estimates. So this would be like a spoiler for your first problem that you were supposed to solve, is that rho epsilon nu epsilon, if you combine the Sobolev embedding coming from this estimate with the estimates of the density, you can show that L infinity L2 gamma plus 1 is bounded by some constant. So again, you can subtract some subsequence such that rho epsilon u epsilon sequence converges to something, to some weak limit, of course, weak star or weak limit, but it will converge to, so rho epsilon, u epsilon, will converge to what? Will converge to some object that sits in this space, but I don't necessarily know that this is rho u. I will denote it rho u bar, okay? So it converges to rho u bar, weakly star in L infinity L2 gamma plus 1. And of course, u epsilon converges again to u, but only weakly in L2 W12, right? The gradient of the velocity in particular converges weakly in L2, L2. Okay, that's all I know. Weakly. And I have multiple nonlinearities. So what are the problems now? Problems. First problem is to show that rho u bar is really equal to rho u. Okay? Once I solve this problem, I have similar problem to show that lim in the convective term, u epsilon, tensor product u epsilon, when epsilon goes to 0, in some sense, so this limit is in some sense, well, we know that probably in a weak sense, this will be something like rho u, tensor product u, there will be some object, but the problem is to identify this object with the product of limits, okay? The same as here, okay? So this is problem 1, and this is problem 1 prime. Very similar problem. Identify this nonlinearity. Problem number 2 is to show that P prime, so maybe, did I denote it already? So I know that P of rho epsilon, right, is equal to rho epsilon to power gamma. It converges, again, weakly, in some sense, this you will deduce, to something that I denote rho gamma bar. But I don't know if this is rho to power gamma, right? If it's nonlinearity applied to my actual limit. This is something that I need to prove. And in the remaining 5 minutes, I'm going to explain you how to do it. Yeah. So first of all, let's start from here, because it's a nice warming up problem. What can we say? Well, we have a sequence U that converges weakly, sequence rho that converges to weakly, so there might be some problem with identification of that object. But you see that you kind of know that there is some compactness for this sequence approximating the velocity coming from the estimate of the gradient, right? So if you now try to do this argument for any time, you forget the dependence on time, let's assume that there is some smoothness there, you have this compactness with respect to space that could be probably used to compensate for the lack of compactness of the sequence approximating the density with respect to space, right? So you have this kind of, at the level of space, you have this kind of matching regularity of the functions. Weak convergence with respect to space of the density, stronger information for the velocity. No, but you have the same thing actually happening for the time. Now, why? Well, for that, I use this observation that my sequence, okay, it converges, the approximating sequence of the density, it converges weakly with respect to space, but with the strong topology of the, well, not strong topology, but in C. It's a continuous function. Moreover, I control the time derivative in something that is exactly dual to that space. All right? So I have enough of compactness with respect to time for the density that I can use to compensate for lack of compactness with respect to time of the velocity. Velocity is only a L2 function with respect to time. And then, using some sort of Lyon's lemma, it's a famous Lyon's 5.1 lemma from the book, or something like a Diffie lemma. I don't know if you learn about it. Diffie lemma, a simple version of Diffie lemma. You can identify this limit. So that's checked. Now, I claim that this problem 1' is very similar, indeed. And now I will tell you why, introducing my notation. So now I know that this object has a limit that I already identified. But I also claim that my m epsilon has a time derivative that I control. I go back to my momentum equation, I put everything on the right-hand side, I use my a priori estimates to get very similar and negative Sobolev spaces bound for the momentum. And now I treat my momentum like I did treat the density in the previous step, and I identify this limit like that. Again, the same argument works. But you have to do it one by one, the step one by one. The real problem is here. The field method is here. What to do with that? Well, the genius of Pierre-Louis Lyons, but actually already people like Diperna and Jacques-Louis Lyons, or Czech school of Novo and Novotny, was to show that you have compactness, but not of the function of the density. That there is some combination of the density and divergence that is compact. Yeah? And this comes from looking at this equation long time and coming to the basic principles. This is your force. This is something that will regularize the flow, if anything, the whole force, not the pressure, not the Laplacian separately, the whole force. So the key idea here is to show the compactness of the effective viscous flux or effective pressure I'm going to write effective pressure and combine it with the Diperna-Lyons transport theory, so with the renormalized notion continuity equation to show that for some nonlinearity, and this will be very specific nonlinearity, low log rho, you can remove this bar. You first start with removing the bar, not for your targeted nonlinearity, but for something like that, rho log rho. And then if you have it, this is a convex function of the density. You have convergence almost everywhere of the density. And with boundedness of the norms of the density, this gives you strong convergence. And this will be the end of the proof. The whole theory, the whole beautiful theory is here. This is a quite complex argument. And I usually teach the whole term of my students to explain what it does. This is a beautiful technique. Now I promised some problems. So let me say what the problems are. First problem you already know, the nonlinearity in the pressure, right? And second problem. So if you want to publish an Annals of Mathematics, which doesn't happen in PDE community that often, I'll write the problems here under the system. Second problem is I'm very particular about the form of the functions that I took of the pressure and the stress tensor, right? Second problem that was partially answered was what happens if this pressure is not rho power gamma? What can go wrong? Well, in particular, if this is non-monotone function of the density, this argument of the effective viscous flux of this compactness, I didn't mention it, but this part here, comparison of these two techniques, uses heavily the fact that the pressure is a monotone function. If you have no monotone function, this argument doesn't work, and the biggest nonlinearity is not identified. So to do something like that, to some non-monotonicity of the pressure, which is between two branches of, let's say, rho to power gamma, so this would be your pressure. This grows like rho to power gamma, this grows like rho to, maybe actually I could take rho to power gamma plus some constant here. Yeah? I control my nonlinearity like that. For something like that, for this kind of nonlinearity, there is a work of Bresch-Jabin, a beautiful but very complex compensated compactness technique related to our topic, from a paper from Annals from 2018. Okay? And based on this technique, you can really solve more physical problems in the mathematical fluid mechanics. Okay? Second problem that happens is that there is another source of trouble. Somehow we use the fact that this is almost like a Laplacian. So the whole equation is almost like a heat equation. What happens if I let some more physics into it? What happens if the stress tensor depends on the temperature or on the density? Yeah? So if you let the stress tensor depend also on the temperature, yeah, there is a series of works of Czech school originating from the, again, book of Edward Feiereisel and Antonin Novotny, who showed that if the viscosity coefficients, I didn't introduce them, but if some constant that modulates how the stress depends on the symmetric part of the gradient and the bulk viscosity, so the divergence, depends on theta like square root of theta. And if theta satisfies Fourier law, so something like parabolic equation for the temperature, then there is no problem. Really, the whole theory of weak solutions, although it is like a very tedious generalization, it's really the main ideas behind are the same. So this is something that is done, at least for certain forms of Fourier law, certain forms of viscosities, and so on. The big problem, the big problem, in my opinion, is what happens if this tensor depends on the density as well. Because density is our enemy here. It satisfies the continuity equation. There is no Laplacian here. There is no regularizing effect. So whatever nonlinearity involves density here, there is a problem. And again, we have some a priori estimates for systems with a stress tensor, including the density. I'm talking about meaningful dependence on the density. So this means that stress tensor disappears when density is equal to 0, okay? So is equal to 0 on the set where rho is equal to 0. Yeah? So if you assume certain form of the stress tensor, you obtain actually some better estimate for the density. A little bit tricky, in a little bit tricky way, but you again extract information about the gradient of the density this time from the stress tensor, not from the continuity equation. You always have to win about something about the density from the momentum equation. And that's what you do here. And it's the so-called Desjardins estimate. The problem is this Desjardins estimate is a very limited form of stress tensor, very limited form of dependencies on rho. So can you do something for general dependence on rho? General meaningful dependence on rho. Can you generalize this kind of observation? Can you create some hierarchies of energies or a priori estimates for systems like that that would allow you to find the right language for the solutions? So 3 very nice, very difficult problems. The 4th one would be maybe some anisotropy, which we would be very interested in. Anisotropy means that the stress tensor depends differently in different directions. Again, not very much solved. A little bit talked about in this paper from 2018, but it's like incremented improvement, right? Okay, so I will stop here. Thank you very much.